All right, so exam 2 is going to be a week from Thursday, April 1st. That is not an April Fool's thing. It really is April 1st. And I put in the announcement what all would be on there. It'll be 3, acid-base chemistry, 6, mechanisms, reaction energy diagrams, whatnot, 8, addition reactions, which we're going to do today, 14 and 15. Okay, so also I cheated you guys out of an office hour yesterday. Apologize for that. I got a shingles vaccine, and that was worse than Pfizer 2 by a lot. Anyway, I think my head is, I'm still a little foggy, a few drugs, so this should be a good class. Anyway, I'm going to replace that with something in the evening this week. Got to work on my schedule. Probably will be Zoom because I can't get a room that will fit everyone. But if you're having questions about the office hour would focus on spectroscopy and acid-base. But one more time on the spectroscopy, focus on sort of, here's a spectrum and a bunch of molecules, figure out which molecule, or which, match them. Wiley Plus, the one kind of problem that will not be on exam 2, it will be on the final, maybe some on exam 3, is going to be where you just get a set of spectra and you have to sort of come up with the molecule all on its own, right? I'm not asking that one yet. Before you do that on the final, you'll also do it in lab. So everybody should at this point have seen that in lab, you're going to have this assignment where there are unknowns that you have to put together. All right, so today we're going to start chapter 8. And again, if you missed that, if you look at the calendar as I initially suggested we would do it, we were going to go from 6 to 7. We're definitely coming back to 7. But 7's a really thick chapter, a very long chapter. And I think we can finish most of 8 this week. And then that goes on the exam as a unit, and then we can do 7 for exam 3. Okay, so am I recording? I'm recording. So last week, right? Last week I put up Bronsted, we talked about Bronsted acid-base reactions that look like this, right? You have a base, and the base has got electrons, all right? So the Lewis theory of acid-base chemistry is really what you want to focus on in understanding what is a base and what is an acid. The base is going to have electrons. Now, normally those electrons are going to be, you're going to see those electrons as a lone pair or a negative charge, but they can also be bonds. Right, so here Bronsted theory, the acid has the proton, so the proton donor is the acid. The proton acceptor is the base. You can also view it as the base being an electron donor, and that's going to get us our curved arrow. Just a reminder, right, that curved arrow means 2 electrons are going from where the arrow starts to where the arrow ends. And then H can't have 2 bonds. So the 2 electrons in that HA, the HA bonding electrons then, right? You get a curved arrow that starts with those electrons and goes to the A. That makes a lone pair on the A. All right, so Lewis is a more general theory. Any Bronsted base is also going to be a Lewis base. Any Bronsted acid is also going to be a Lewis acid. But there are Lewis acids that are not Bronsted acids. There are Lewis bases that aren't Lewis bases. So in chapter 8, we look at reactions that are called addition reactions. And these are going to be additions to alkenes. All right, so I'm just going to use cyclohexene as an example. We've got this carbon-carbon pi bond, and we're going to add something to that. All right, Right, so this is an example of an addition reaction. The two things add to one another. Now, like the first half of chapter 8 leads really naturally from acid-base chemistry. So, and that's pretty much, those of you here today are fortunate that that's what you're going to see. The second half of chapter 8 are just a whole bunch of reactions with alkenes that have kind of passing resemblance to acid-base chemistry. And so I was asked at the beginning of class how far we would get in chapter 8. That'll kind of depend on Thursday. But there's quite a few reactions in chapter 8 that you wind up just memorizing because the mechanisms are bizarre. They're not bizarre. They're not related to acid-base chemistry. But today we're going to focus on acid-base kind of reactions. So if you look at this, if we take this alkene, what is that, 2-methyl-2-propene. No, 2-methyl-1-propene. 2-methylpropene. If we add HBr to this, we get this product. That's just a bond. You might wonder where the H went. Let me redraw this. You don't need to erase anything. Blue is dying. All right, so this is an addition reaction. We add HBr across the double bond. That's how we would phrase that. You might think about the energetics of this. The carbon-bromine sigma bond is quite weak, but the carbon-hydrogen sigma bond is pretty strong. A pi bond is weak relative to a sigma bond. In general, this doesn't always work, but in general, if you have a reaction where pi bonds are being exchanged for sigma bonds, that reaction will be downhill, right? Because you're going to make stronger bonds. On the other hand, entropically, so I guess I should write some stuff down. All right, so the bonds are stronger in the products. We've exchanged one pi bond. You break a pi bond, you break an HBr sigma bond. The HBr sigma bond's fairly strong. And you turn it into a CH sigma and a CBr sigma. Really, the sigma bonds to the bromine, pretty much equal. But exchanging a carbon-carbon pi for a carbon-hydrogen sigma is way downhill. Right? That carbon-hydrogen sigma is a much stronger bond. So that's delta H. Right? But the left, the starting materials, is more disordered. Why is that more disordered? There are more molecules. You got two molecules, right? So they can go wherever they want. I mean, they got to stay in the flask unless you spill it. But in theory, the HBr and the alkene can just go any which way they want. Totally random. They're not tied to each other. Mathematically, what we call this are degrees of freedom, okay? So you've got way more degrees of freedom. You could have all the alkene on one side of the flask. You'd have all the HBr on the other side of the flask. You could have them switch places. You could have them intermixed. On the product side, there's one molecule, right? The H has to be within bonding distance to the carbon it's bonded to. The Br has to be within bonding distance to the carbon it's bonded to. It's way more ordered, all right? So this is delta S. So entropy is going to favor the left. Enthalpy is going to favor the right. And it's going to work out that this reaction sort of depends on conditions. Remember, entropically favored reactions are favored at higher temperature. right? So the overall equation here that I asked you to learn last week, and again, I'm not going to ask you to, I don't want you guys mathematically, quantitatively solving these equations in this class. By the time you graduate, this is an important skill to have. Math is very useful. I just want you to use that equation to think about it, right? So that equation and what I've talked about in terms of order and disorder and bond strength, what that tells you is as the temperature goes down, the entropic factor is less important. So at a lower temperature, you favor the right. As temperature goes up, you would favor the left, the entropically favored side. The other thing that comes into play then is Le Chatelier's principle, which is if you add more to one side, you push it the other direction, right? So if we want this reaction to go to the right, we would usually use an excess of HBr. Right? If I pump in a whole bunch of HBr, I'll shift the equilibrium to the right. If somehow I suck out HBr, what would suck out HBr? What kind of molecule is HBr? It's an acid. So what would I put in to suck that out? Base. Right? So if I add a base, I pull this out, the reaction shifts to the left. So actually, right to left in this equation, adding a base, that's chapter 7. All right? That would be an elimination reaction going to the right. So this is an addition going left to right. It's an elimination going right to left. Remember, left and right is pretty much a human construct. These molecules don't know they're in an addition reaction. They don't know they're in an elimination reaction. They're just trying to get to the lowest energy point they can, trying to get the most comfortable. Okay. So a couple of questions you might ask here. Well, I've talked about sort of why the reaction would go one direction or the other. And that's always going to come down to entropy, enthalpy, and Le Chatelier. The other question you might well ask is, these two alkene carbons are different. And I've only shown one product. I've only shown the Br adding here to the more substituted carbon. I've shown the H going on the less substituted carbon. You might ask, couldn't that go the other way? And the answer is no. It won't go. In this reaction, it will not go the other way. We're going to go through what. And then the next question to ask, I've got to find a decent blue pen. The question that organic professors have been asking organic students for 60, 70 years now. And really, this is the way organic chemists think about reactions. What's the mechanism? How did it happen? All right, so in the acid-base reaction up top, this is the proton transfer is a single step. Right, so there's just two arrows. Reactants turn into products. An awful lot of reactions, probably most chemical reactions, are multiple steps, multiple elementary steps. All right, so the mechanism here. You guys identified HBr as an acid. Yeah, right? Acid. Drugs, man. I'm actually a lot more sober than I appear. But last night, if I had been at office hour, my wife laughed at me pretty good that I told her I was supposed to be at office hours at that point. Went to bed at like 5:30. That's always fun. Okay, so you've identified HBr as an acid. What's that going to make the other molecule? What are the most reactive electrons in the base? What are the highest energy? The pi bond, right? So I've said that a pi bond is weaker than a sigma bond. And this is kind of a fundamental thing. And this comes back to kind of first principles guess this should be a C, really. Right. So if you have a carbon-carbon sigma bond, you've got like two sp3 or two sp2 or an sp2 and an sp3, but that bond is directly between the two. Right? It's two orbitals that can fully overlap. It's the difference between a handshake and a high five. Like if you're going to latch on to something, you're going to reach for it directly. You're not going to like, you know, reach up here for a rope that's tied to it. The pi bond, so this is a sigma bond. And these are phased. Hopefully you saw some of that in the spec module in lab, right? The 2p orbital has a positive lobe and a negative lobe. The book will sometimes show that as black and white, red and blue, whatever. It's really plus and minus. And it comes out of the solution, the mathematical solution of the differential equations for the 2p orbital. I said differential equations, and I probably lost 3/4 of you. That solution is a square root. Okay, so just like 2 is the square root of 4, minus 2 is also the square root of 4. So you get one lobe that's plus, one lobe that's minus. If the two orbitals come together to where the plus lobes are overlapping and the minus lobes are overlapping, they reinforce one another. They actually, the sum grows a little bigger than just the two by themselves. If they come together out of phase, plus with minus, minus with plus, they actually destroy one another, and the resulting sum is less than the two by themselves. All right, but again, that overlap, it's an overlap, it's a bond, it's a positive interaction. But it's not nearly as strong as a sigma bond. So yeah, the pi bond is the highest energy, is usually going to be the highest energy electrons in an alkene. That's going to be the nucleophilic. Those, right? So we talked about HOMO and LUMO in the. So if we just look at this, I don't know how I'm going to, yeah. So hopefully you got this from that UV bit. We've got the HOMO, which is the highest occupied molecular orbital. We've got a LUMO, which is the lowest unoccupied. For ionic reactions, those are the two orbitals that matter. Right? If a molecule is going to give electrons away, those electrons are going to come from the highest energy, least stable, either bonding or lone pair. If a molecule is going to accept electrons, the electrons that come in are going to go into the lowest energy orbital. Right. Okay, does that make sense? So, as you look at this, there are no lone pairs in this molecule. There's a bunch of sigma bonds, so sigma electrons, and there's a pi bond. And so the pi bond will attack the HBr. And again, this is just a proton transfer reaction. Pi electrons attack that H. H can't have two bonds, so the HBr bond breaks. The lone pair goes to the Br. So from those arrows, draw me what you get. Draw the products of those two arrows, the two curved arrows. So one of these is pretty easy. The Br is bonded to an H, but that HBr, this arrow, kind of the second arrow here, right? And it's not drawn from the H, it's drawn from the bonding electrons. So this arrow starts with these electrons and goes to the Br. That bonding pair is going to turn into a lone pair on the Br, right? So that's going to, and if Br here is neutral, if something's neutral and it gets more electrons, it's going to become negative. If something is neutral and it gives away electrons, it will become positive. So Br minus is going to be one of the things you get. You can put the 4 lone pairs there if you want. And now the trouble with that alkene, like I said, the alkene's neutral, it gives away electrons, so it's got to become positive. But the pi bond, the basic electrons in this molecule are shared. But after the reaction, they can't be shared. One of those carbons is going to get an H, and one's going to get a positive charge. All right, so if you followed this, right, if you looked at what we get over here, probably at home you couldn't see that because the pen was dying. All right, so the Br ends up on the positive or on the more substituted carbon. That's probably the one, well, that's, right. The H ended up on the less substituted carbon. So you put the H on the less substituted carbon first. I see some people erasing. I don't know if you're making notes. Really, like if you haven't read chapter 8 or the relevant bit of chapter 6, like there's no reason necessarily to know which carbon gets the H, which carbon gets the plus. So the question becomes then, why does the H go here and the plus go there? And we'll talk about that in just a second. But first, draw a curved arrow or arrows that get us from the carbocation and the bromide ion to the product. Okay, so it's only going to take one arrow. The arrow is going to have to start with a bromide ion, right? So I will go ahead and draw in the lone pairs here. Bromide ion's got the electrons. It's got a negative charge. That's the thing with the electrons. That curved arrow always starts with electrons. Then it goes somewhere else, either to a positive or a partial positive charge. All right, you can't start an arrow at a cation. That cation is notable for not having electrons. So you're not going to start an arrow there. So the arrow's just, you're going to have one arrow that makes a bond, like so. And what that basically means is the electrons in that bromide ion are going to come in and collide with the vacant p orbital on that cation. All right, so now is when we need to talk about carbocations. Right, so positive charge is a cation. It's on a carbon, carbocation. What's the hybridization of that positively charged carbon? Got to vote for sp3. People hearing the suspicion in my voice vote sp2. Anybody for sp? How many things is it bonded to? What's the hybridization of things bonded to three things? It's sp2. All right, so if we look at this, if you look at the shape of the sp2, it's trigonal planar. Great. All right, so it's bonded to three things. That sp2 carbon is bonded to three things, and then it's got this vacant p orbital. So the p orbital's there, and I don't know about you guys. This was the thing that took me forever. I mean, I still screw this up thinking about stuff. It's easy to forget. Orbitals exist independent of electrons. All right, you don't have to have electrons somewhere to have an orbital. It's not like hydrogen is just a proton and then all of a sudden there are orbitals when electrons show up. Hydrogen, which only has in its neutral form one electron, has a 5s orbital and a 6d orbital and a 4p orbital. It's got all these different orbitals, just there are never electrons in it. So there's this p orbital on the carbon that doesn't have electrons in it. And that's what I mean, that's now the LUMO. So if bromide's going to put electrons in, right, this is, the second step here is just an acid-base reaction. It's not a Bronsted acid-base reaction. There are no protons going anywhere. But this bromide is an electron donor. The carbocation is an electron acceptor. Right? So bromide's got 4 sort of equivalent lone pairs. That's going to be the HOMO for bromide. And then, I guess it's an atomic orbital, sorry. What would that, HOA? 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 Anyway. So then one of those lone pairs is going to be donated into the lowest unoccupied orbital in the cation. That lowest unoccupied orbital is going to be the vacant p orbital. This orbital would really like to have some electrons. And during that transition, the carbon's going to go from sp2 to sp3. All right. So the question then is, like if we come back over here, where am I going? All right, that was the cation that didn't form. Right, if you just, like I said, if you just come in here and you don't know anything about carbons or carbocation stability or anything like that, you got an alkene, you got to put an H on one, you got to put a positive on the other. It's 50-50, right? It's a coin flip if you don't know anything. And so when I say this is the only one that forms, I don't mean this is the only one that forms like 80-20. I mean this is 100% the only one that forms. So this doesn't form at all, and the question is why? And it all comes down to the stability of the carbocation. Right, so I'll give away the game. I won't tell you why, but I will tell you that this cation is way, way more stable than this cation. Positive C. Most stable carbocation. I don't know why that word, I've been talking about it over and over. All right, that's the most stable possible carbocation. And the reason, well, how would you stabilize a positive charge? What would you use in a molecule to stabilize a positive? You could delocalize it, but more specifically, what are you delocalizing? Like what, John, what were you going to say? Yeah, so electrons, right? If I've got a positive, I'm going to stabilize the positive by giving it electrons. So obviously, you know, if one way of stabilizing it would be to have the bromide come in and give it electrons and make a bond. That works. But that's not really what we're talking about. We're talking about why is one cation more stable than the other. And it turns out that this cation has more electrons available to it than the other cation. And that's not really immediately apparent. Delocalization is really important too. So if you can have carbocations that are resonance stabilized, resonance stabilization is really important. So as we look at this carbocation, think about, I'm going to now draw it down here. All right, so here's our carbocation. Got a vacant orbital there. Where do the electrons come from to stabilize that? And where they come from are the bonds next to it. Right? So there's a CH bond. I'm going to pick one. So there's just a CH bond on the carbon next to the carbocation. This bond is electrons, 2 shared electrons. Okay, so that H, these electrons can overlap with that p orbital, right? So I've got this orbital over here. It's got 2 electrons in it. I've got a vacant orbital here. And it just sort of ties it down a little bit. It's not a real, like, the CH bonding electrons they're involved in just keeping the H and the C bonded to each other. So they can't be totally given to that positive charge. But they can help out a little bit. The more of that you have, the more stable the carbocation is. And if we look at this, on this carbocation that I say forms, right, we've got the one I showed here. We've got three different things three different carbons bonded to the carbocation. Each of those carbons has 3 hydrogens on it. And it doesn't have to be a hydrogen. It could be another carbon, right? So it's just going to be a bonding pair of electrons. The tertiary carbocation has 9 different bonding pairs that could contribute to that. The primary, right, 2 of these bonds are to H. The H's have no more electrons. So this carbocation only has 3 here. Question? Yeah. It can. And yeah, that's a very perceptive question. If there's something that can come and take this H away, like a base, so if a base came and took that H, then you can make a double bond. But as long as that H is there, you get this weird thing, and they tell us not to tell you guys about it. You get this weird thing called a 3-center 2-electron bond. And it does produce some very weird results. So really what happens is you've got a bond between the H and both C's, but there's only 2 electrons holding those 3 atoms together. And the other thing then is, like I said, this is a fairly weak interaction. It's enough to make this way more to make the tertiary carbocation more stable than this primary. But it's not like it just holds here, right? This bond is continually rotating. So it kind of slows up here, and then it'll rotate, and another one will donate some electrons. It's this weak stabilizing interaction. Question I meant to ask, and I didn't. If we just look at step 1 here, so we're just looking at going from the starting materials to the cation, which side is favored? The cation, not the final product. Yeah, the starting material by like a bunch. All right, so here's what I'm kind of jumping. Let me finish up with cations, and then I'll come back and talk about the reaction energy diagram. So, carbocation stability. All right, so a tertiary carbocation is a good bit more stable than a secondary, and a secondary is quite a bit more stable than a primary. And methyl cation, I don't know if you guys on the left side of the room, your right side of the room can see that. A CH3 plus really doesn't form. You're never going to get CH3 plus under normal circumstances, because like there's nothing stabilizing that plus at that point, right? All right, so if your alkene gives you the choice between a tertiary cation and a primary, tertiary wins hands down. Tertiary versus secondary, tertiary is still going to win. Secondary versus primary, secondary is going to win. This original one I showed right here, if X and Y were HBr, plus and plus, I mean they'd both be secondary, right? Then it doesn't matter. Delocalization was mentioned. So right? If you have a double bond bonded to that plus, right? So now you can get a resonance structure. If you can delocalize that positive charge, that's going to be a benefit. And then the question about the double bond was a good one. if you if you have an atom if you have an atom bonded to the carbocation that's got a lone pair, right? Not a bonding pair, but a lone pair. This is very good stabilization. Right? So if you have an oxygen there or a nitrogen, something like that, now that lone pair can make a double bond. You're exactly right. So your question was exactly right. That interaction makes a double bond if it's not involved in another bond. And you can put all this stuff together, right? You could have a tertiary resonance stabilized that's got an oxygen on it. That's going to be a really good cation. You can have a primary with nothing else. That's going to be a really bad cation. So figuring out like what the most stable carbocation is important. Yep. Yeah, I'm just saying, like, basically, I guess I didn't give this as a ranking, did I? Right, so if we have so if you just compare two cations, one's got an atom with lone pairs. And I say an oxygen here. Honestly, I should draw it like this. Any atom with a lone pair, right? Because now, what you guys said, right? To stabilize a positive charge, I want electrons brought in. The best thing you could use with electrons would just be a lone pair that's not tied up anywhere else. All right, so you guys are going to be able to need to rank cations by stability. Right? If I give you two cations, you should be able to tell me which one's more stable. And that will come up in these addition reactions, the first few addition reactions in Chapter 8, where the reaction goes through a carbocation. It's always going to go through the more stable carbocation. Let me put that up. All right, so any reaction that goes through a carbocation will always go through the most stable carbocation. If the reaction involves a carbocation, the most stable carbocation is the one that will be used. So that's why when we do this first addition reaction, right, we're going to protonate the alkene. Look at the mechanism over there. I guess I could come over here. Protonate the alkene, we get a carbocation. You've got to get a carbocation either way. The H cannot bond to two things fully. So it's either going to bond to one carbon and the other carbon be plus, or vice versa. So one of those carbons has to be positive. It's always going to go through the most stable. So we're going to get the tertiary carbocation. It's tertiary. I don't know if I explained that. This carbocation is tertiary because the carbon that's plus is bonded to three different things, three different non-H things. This carbocation is also bonded to three things, but two are protons. So this kind of goes back to primary, secondary, tertiary alkyl chlorides. A tertiary alkyl chloride, the carbon that's got the halide is bonded to three other carbons. We sort of treat H as the default, right? Carbon's got to have 4 bonds, so just like we do line structures, we assume anything not shown is an H. So tertiary, secondary, primary all comes from like non-H things. Yep.
So when you drew that, like, that didn't have enough of primary, right?
This is a primary. Yeah. So this is tertiary. This is primary. And this reaction does not happen. All right. My board's getting kind of crazy looking. So for this reaction, we're going to change gears a little bit. I'm going to make you do something. For that reaction in the red parentheses, draw a reaction energy diagram. So now that you've spent a minute, if you're wondering what that is, a reaction energy diagram, you're going to plot the energy, that is stability, versus some arbitrary reaction coordinate. Basically just going left to right. All right, so far you guys have seen reaction energy diagrams just for the acid-base reaction, right? This is a single-step reaction. In a single-step reaction, you're going to have one transition state. You're going to have reactants, transition state, product. In a multi-step reaction, there will be an intermediate. We'll call this thing here is the intermediate. And like I said, I asked you guys, like, just looking at the very first step of this, alkene plus HBr goes to carbocation, you know, which is favored? By far, the starting material is favored there, right? Every atom has a full octet, everybody's neutral. You've got like 2 molecules you can put in a bottle. This is one where I think, you know, you all, you're at a, not this class only, but Orgo students are always at a bit of a disadvantage. I have this like in, you know, long decades of experience of like what compounds can you isolate and what compounds are you not going to be able to isolate. So this alkene, the HBr, the final product, terbutyl bromide, all of those are things I can buy, I can put in a jug, I can put on a shelf in my lab, I can go away from 20 years, and they're all still going to be there. That carbocation cannot be, even a stable carbocation cannot be isolated. Like when I say that carbocation is more stable than the primary, it is. That doesn't mean it's a stable thing. And I think you would, you know, you can kind of look at that. One, there's a charge. Everybody always looks at charge. And I've had some good questions about, you know, and it is one that I think always bugs students. Charge is not always bad. Sometimes charged molecules are more stable than their neutral counterparts. But that's because charge isn't the end-all of stability. A full octet really is. It's going to be really rare to find a molecule that's stable enough to be isolated where there are atoms that don't have a full octet. Okay, so if you look at this, in the carbocation, the carbon that's got a positive charge only has 6 electrons. It's sharing 6 electrons, so it doesn't have a full octet. Molecules that have atoms without a full octet tend to be really reactive. Okay, so as you think about this, we're going to put reactants on here somewhere. And products, I'm going to draw products, I don't know if you can tell that, they're slightly downhill. All right, like I said, and that's going to depend on the temperature, coming back to this whole discussion of enthalpy favors the products, entropy favors the starting materials, the reactants. I haven't told you what temperature to draw this reaction energy diagram at. It matters. Basically, neutral, isolable compounds have roughly the same stability. Like one's going to be a little more stable than the other, but not by much, and certainly not compared to this molecule in the middle. Right? All right? The molecule in the middle, the intermediate, is way high in energy, much higher than either the reactant or the product. Does that make sense? Right? The reactants and the products, stable, neutral, everybody's got a full octet, isolable. Intermediate, not that. So now your reaction energy diagram will connect reactant and intermediate like so. And this should really be a curve probably. Right? So an intermediate is defined as being a local minimum. So that carbocation, even though I can't isolate it, I can detect it. So if I go take an NMR, I could possibly see the cation by NMR. I could see it by UV vis. I could detect it. We've got this other thing that I haven't really talked about much. And there are two of them here. So every single step, every elementary step in a reaction will have one transition state. That transition state is just defined as the high energy point between those two detectable molecules. In a single step reaction, like an acid-base reaction, a proton transfer reaction, there's one transition state. We're going to see reactions that have 2, 3, 4 intermediates. Okay, so you can have multi-step reactions that have lots of intermediates. All you want to try to do when drawing a reaction energy diagram for this is just get the relative energies roughly right. Right? If we said under all conditions this reaction would favor the products, right? This original reaction, if that would always favor the products, then the product needs to be significantly, noticeably lower on the diagram than the reactants. But all the intermediates between would be higher. If we had a reaction that went through a secondary and then a tertiary cation, the secondary should be higher. Right? So basically you just want to use what you know about molecular stability to plot the different things. And then, this curve, a fast reaction would have a lower transition state than, well, actually I can use that. So if we look at this diagram, right, which step is the slow step? We got two steps. Which step is the slow step? The first one, right? The energy of activation is there. So that's the first energy of activation. The second energy of activation is there. And if I'd given you guys a little time to think about this, this makes perfect chemical sense. Kinetics won't always make perfect, logical sense. But here you're talking about two neutral molecules, proton moving, a bond breaking. You wind up with a carbocation. Again, you're going to have a carbon that doesn't have a full octet. So you're going to go from two isolable molecules to a molecule that doesn't have a full octet. It's going to be slow. Like you would guess that would be slow. And then if you look at the second step, I've got a molecule that doesn't have a full octet and an atom that's got an abundance of electrons, and they're going to make a bond so that all the atoms have a full octet. That should be fast relative to the first one. Like I said, it won't always make perfect sense, but this one pretty much does. And you can see that. So if you drew like a little hump on the first one and a giant hump on the second one, that would be off. So it's a qualitative depiction of stuff that, and then like I said, if you're so inclined, you can go in the lab and you can work out all the numbers and you can get a really perfect, quantitatively perfect graph here. But that's not what we're going to do. Questions about the reaction energy diagram? Yeah, sorry. Here? A, energy of activation. Yeah. 20 minutes to go. Who's had lab so far this week? Did you get plexiglass? Okay. Was it cool? Some of anyway, you're making plexiglass. We've been discussing how much this would add to your life experience. I hope a lot, but all right. So let's do a give me the product of that reaction. If you get the first one, give the second one a try. And if you get both of them, go ahead and draw mechanisms for them. Okay, on the first one. Again, it's an addition of HX. I should have said this. Like, this is the first reaction in chapter 8, addition of HX, then addition of X2, and then, it sort of progresses. And like I said, by the end of the chapter, it's just we're adding things. The mechanism doesn't matter. It's just stuff goes on there. So here, HX is always going to go through a carbocation. And like I said, it's always going to go through the most stable carbocation. That's a rule. We have this rule called Markovnikov's rule. Markovnikov was a 19th century Russian chemist. And he's the one that figured out in a reaction like this, HX with a double bond, that X always goes on. What he observed was X always goes on the more substituted carbon. All right, that is technically Markovnikov's rule. He never, He discovered this sort of before we even knew there were, you know, tetrahedral carbons. Like, this is really early stuff. The reaction I like you guys to learn is more that if a reaction goes through a carbocation, it goes through the most stable carbocation. Because here, the cation we're going to get either way is secondary. So the first step, draw the two cations we could get. Right? Those are your two cations. So the H is going to go on one carbon, the chloride is going to go on the other carbon. Which of those cations is more stable? Left or right? Why? Yeah, so it's delocalized. Right? So we've got a double bond that can resonance stabilize that carbocation. This is called a benzylic carbocation. So if you have a carbocation on a carbon bonded to a benzene, those are actually really stable. Even a primary benzylic cation is quite stable. Yep.
How you know that it's in the carbocation's in the substituent and not the benzene ring?
No. This always gets me. This is like, one of these days I'm gonna teach this class right. But not now, all right? Like now, it's not 2020. I was gonna say 2020 is a weird year. It's always 20, the rest of my life is 2020. Here's a big, this is like loud, this has to be a huge thing. All right. Now, at about this point every year, every time I do Ergo 1, I'm like, this really should be in chapter 2. How many alkenes are in that molecule? There's some fuzzy answer. And I've kind of built this up, right? This is, everybody's like, well, 3, but that's clearly not the right answer. Yeah, so there's this resonance, it's resonance stabilized. And the real structure is this. Like the 6 pi electrons are sort of delocalized all around the ring. It's even worse than that. Like, not worse, better. When you guys take Ergo 2, depending on who you have, you'll go into this in more or less detail. But the upshot is there are no alkenes in that molecule. All right? A benzene is not an alkene. So these 3 double bonds are not alkenes. No, this is a great, I'm really glad you asked this question because this would have been about 40 emails next week. So here, like, I don't know how many of you did this. It wouldn't surprise me, totally, it's fine if you did this. Today, it's fine if you did this, right? If you put HCl adding there or here, like, ooh, that's the most stable substituted one. A benzene is an aromatic molecule. That word actually comes out of, benzenes smell nice. Like, I love the smell of benzene. It's a carcinogen, don't smell it, but it smells really nice. Aromatic molecules now, to a chemist, when we say aromaticity, we mean it's got this special quantum mechanical stability. So it's even more than it's just like normal delocalization. I think at this point, everybody in here knows conjugating double bonds, resonance stabilization is a thing. But with a benzene, it's even bigger than that. You actually get more than just your usual amount of resonance stabilization. So aromatic molecules tend, well, they will react. It's not like they're rocks, but they don't react as well. So when you look at this molecule, and like I said, I look at this and I'm like, there's an alkene and a benzene. There's only one alkene in that molecule. It's the one conjugated to the benzene ring. So the benzene's not going to do any chemistry here, except for it's going to stabilize the cation that you get out of this, right? So, and at the end, so then you might say, like, if you draw the resonance structure, so I have this one electron, or I have this one double bond moving, right? Now you've got a positive charge in the benzene ring. And you might well ask, well, why doesn't chloride attack that carbon? Right? There's going to be positive charge here, here, and there, sort of alternating around the ring. And again, just thinking about Lewis structure, you would say the chloride could attack any of those carbons. Would make a lot of sense. But there's a really high quantum mechanical preference to having a benzene still, like having that molecule be a benzene at the end. All right, I don't want to beat this horse too much, but basically, benzenes don't do these reactions. Who asked that question? I forget. Yeah. The answer is benzenes don't do alkene chemistry. Benzenes do chemistry, and they do. We can't add HCl. We can add a chlorine to a benzene, but it takes catalyst in much harsher conditions. All right. So, yeah. Thanks for that. Benzenes. Are not alkenes. So for chapter 8, benzenes just won't do any addition chemistry. And like I said, I think this is such a fundamental, the quantum mechanics of it are pretty deep, so we don't tend to do that right at the beginning of Orgo 1. But I should probably write that sentence for you at the beginning of Orgo 1. Benzenes aren't alkenes. Okay, so the product we're going to get this we're going to get that one stabilized, resonance stabilized cation. And so the chloride goes on the benzylic carbon, 1, 2, 3, 4. That would be your product. What is the stereochemistry of that? Is the chloride forward or is it back? What was that? Could be either. So forward, back, either. Any votes on that? Who says forward? Who says back? Who says either? Okay, good. So a lot of hands came up. I thought maybe I'd completely lost you all. All right, so think about this cation again. If we come over here, I think I've right? Carbocation. It's an sp2 carbon. It's trigonal planar. We've got a lobe below the carbon, a lobe above the carbon. If I'm a chloride ion and I want to make a bond to that carbon, I can come in from the top, I can come in from the bottom, either way. There's really no preference for that. So this is going to be a racemic chloride. And it occurs to me all of a sudden that the snow day cost us. Have we done the word racemic in here? Yeah, that's what I thought. I will. After the exam, I will catch you guys up on that, some terminology on that. But basically, if you have a carbocation and it makes a new bond to something, that new bond is going to be racemic. It's going to be 50% attack from one direction, 50% attack from the other direction. All right? All right, on this other reaction over here, give it 60. Oh, sorry.
Do you have to label the H on the card?
Yeah, no, you don't. So the H adds to that carbon, and you get two H's. Could be either of them. You can. Like, I've been putting that H in just sort of to say this H comes in. If it helps you, you can. Like I said way back at the beginning, you can always write one H in, and we'll assume the others are still H's if you don't show them. So if it helps you guys like picture these reactions by drawing the one H in, that's fine. Okay, so take like a minute or so. We'll finish up with this one reaction. Yeah.
Do you always want to show the middle step, or that only for the reaction?
you would only need to show the, yeah, if you look at old exams, like there's going to be a reaction page where I ask for the product. You don't have to show the middle steps, you don't have to show the mechanism, you just got to draw what the final product is. Then there are questions where I'm like, what's the mechanism? In a mechanism, you have to show every elementary step, the curved arrows in every elementary step. You have to explicitly draw every intermediate. All right, I'm going to, in the interest of time, I'm going to go ahead and blow through this. I'm not going to blow through it. I'm just going to not give you as much time as you should to work this out. This is still an addition of HX. You're adding HOH, all right? But that won't happen without an acid catalyst. So you've got to have something that will protonate the double bond to make a carbocation. You could imagine it. I'm going to just put up a, right, HBr is a pretty strong, I'll put up the original. All right, so if I use HBr to protonate a double bond, that's not a favorable process, but it happens enough to get us to the product. Right? We've got a strong acid, HBr, and we make a strong acid. Carbocations are Lewis acid. They're electron poor, they're electron acceptors. They're very electron poor, so they're strong Lewis acids. HBr is also a strong Lewis acid. So you sort of have a strong acid turning into a strong acid. And that, while it's not, favorable, it happens. If you don't have H3O plus in this other one, if we just have water, right? Water is a weak acid, makes a strong acid. The alkene is a weak base, and it makes a strong base. So even though this reaction happens, the reaction I'm about to show a product for, even though it happens, it doesn't happen at any kind of rate where you'd actually observe product unless you have a strong acid catalyst. So this is a hydration reaction. We're going to add H2O across the double bond. So again, the H is going to go in the less substituted. The OH is going to go in the more substituted carbon. So the product is going to be this. And I'll go ahead and put the H in for you. There's the H, right? So the H and the OH add across that double bond. Yep.
Can you put the hydronium floating around?
Well, so for the mechanism, you've got to involve the hydronium. Yeah.
And the OH going between the two methyl groups.
Yeah, sure. That could be the OH and that a methyl. That could be an OH. So one thing is this is not a chiral atom, right? And the other thing is, even if it were chiral, you get 50-50. So, all right. So the mechanism for this, right? This is why you've got to have this strong acid. The hydronium is going to protonate the alkene. So H3O plus protonates the alkene. We get our carbocation. So this is the last time I'm going to put that H in. The H bonds to the secondary carbon. You get a tertiary carbocation. Now, what attacks the carbocation to make water? This is a really important point, and a point that's going to, if you know what the product is, oh, that's the other thing. On tests, like if I ask you for a mechanism, I'm going to give you, like, here's where we start, here's where we finish, draw a mechanism. And you're going to see this, and you're going to think, I'm here, I need to get to there, I'll just have hydroxide attack that cation. But again, there's no way that, you don't have any hydroxide. Right? H is not going to just leap off of water to give you hydroxide. This reaction is being run under acidic conditions, H3O+. That means you don't have hydroxide to play with. So water is going to attack, and that both H's stay on there. Right? So water attacks the electrons on oxygen. Oxygen's a weak base. Sorry, the oxygen on water is a weak base, but it's reacting with a carbocation, which is a really strong acid. So water attacks the carbocation, the H's hang around, and now you've got excess water here. The other thing is, the stuff over the reagents, you've always got more than that. You never have one molecule of anything in a reaction, okay? So you've got a lot of water, you've got a lot of H3O+, you've got a lot of the alkene. So you can always use them more than once. So now, excess water, another water comes in, takes that proton, and gives you the product, and H3O+. This is an acid-catalyzed reaction. That means if it's catalyzed by acid, the acid can't be consumed. You need a little bit of H3O+. That starts you off with the carbocation, and then the water takes you through. And again, Le Chatelier's, if we do this at low temperature with a whole bunch of water, we'll favor addition. If we were to do this at high temperature without any water, we would favor the elimination. I have taken 90 more seconds of your time than I'm allowed. I'll see some of you up in lab. Like I said, look for announcements. There's going to be an evening or a late afternoon, at least, office hour that will be sort of a mix of Zoom and in person. That's it. See ya.